So the last note we're going to discuss in measurement and analysis is we're going to be talking about working with the trig rules and something called proportional reasoning. Trig rules specifically are going to be of concern in the next few units, but proportional reasoning is definitely throughout the semester, and it's a technique that helps us solve problems that appear to have not enough information to actually complete them. But let's start off with the trig rules first of all. If you recall from grade 10, the first basic set of trig rules you should have learned about are those associated with right-angled triangles. And those are the primary trig ratios, and that being sine theta is equal to the opposite over the adjacent, cos is equal to the adjacent over the hypotenuse, and tan is equal to the opposite over the adjacent. Or the easiest way to remember it is SOHCAHTOA. The SO part is sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and tangent over adjacent, SOHCAHTOA. So the important thing, however, is to understand the difference between which side is opposite and which side is adjacent. And that entirely depends on the position you're in. So for example, the opposite and adjacent sides are going to be different for when we're looking at things from the perspective of theta versus alpha. So let's talk about it from the perspective of theta first of all. So from the perspective of theta, the opposite side is literally the side that is exactly opposite to the angle, which is this side right here. The hypotenuse is always the same because the hypotenuse is always opposite the 90-degree angle. So this is our hypotenuse over here. And the last remaining side, that has to be your adjacent side. However, if we're talking about alpha, from alpha's perspective, things are a bit different. This is now the opposite side. The hypotenuse, of course, stays the same, and this is the adjacent. And that is reflected in the trig ratios over here. So sine theta is equal to the opposite over the hypotenuse. The cos of theta is equal to the adjacent over the hypotenuse. And tan theta is equal to the opposite over the adjacent. Looking at alpha, sine of alpha is the opposite over the hypotenuse. Cosine of alpha is the adjacent over the hypotenuse. And tan of alpha is the opposite over the adjacent. So the primary trig ratios are fairly easy to work with, but what we have to keep in mind is that the primary trig ratios only apply to right-angled triangles. What happens when we don't have a right-angled triangle? That's when we have to move into sine and cosine law. So let's focus on what sine law is. And as a review, it is the ratio of the sides to the sine of their opposite angle are equal to the alternate sides and opposite angle of each side of the triangle. So the ratio of the side to the sine of its opposite angle is a constant for a given triangle. And that's where we get this equation here. Alternatively, though, you can actually have it so that it's the sine over the side. And functionally, they work exactly the same. It just makes it a little easier to manipulate the equation algebraically a little later on. And cosine law kind of looks a little bit like Pythagorean theorem, but with this little piece added on at the end here. And there are three versions of cosine law. And that is when you are looking for side C, when you're looking for side A, and when you're looking for side B, or angle C, angle A, and angle B. So you use one of the three versions of the formula depending on the setup of your question. And again, this is just a review of stuff that you would have done in grade 10. Let's start off with an example. So let's take a look at this triangle over here, and let's make sure that we identify the sides correctly. This is angle C, and side C is opposite to angle C. This is angle A, and side A is opposite to that. This is angle B, and side B is opposite to that. So the first thing we need to look for is we're trying to solve for angle B. So when we look, we want angle B. That's what we are trying to find. And here are the things that we know. We know side B, side C, and angle C. So the version of the formula that we're going to work with is sine B over little b is equal to sine A over little a. Now, the expectation I have for grade 11 and grade 12 university prep students is that we manipulate the equations algebraically first. In previous grades, it was common practice to substitute the numbers in after the formula section. So normally what you would have done is you would have written your formula down and then you would have substituted your numbers in. In my experience, it is best practice to practice the algebraic rules, because ultimately being able to work in algebraic space tends to result in better answers long term. Furthermore, if you make a mistake in the algebra, it is much easier to fix a single letter than to have to redo all the math. So one of the things you will note in these videos is that I tend to try to isolate as frequently as possible. It's not always practical to do so, but my general view on things is that one should isolate for the thing that they're looking for using the rules of algebra first and then substitute the values in. So starting off is that our goal is to isolate for angle B. So remember, whenever you're manipulating any type of equation, when you're isolating, you're using Bedmas and reverse. So when you're talking about Bedmas and reverse, I'm referring to what I often refer to as Sam Deb. And what that means is this, is that you take on the addition, subtraction, and additions first in whatever order they come in. Then you deal with any multiplication division, followed by exponents, followed by your brackets, if there are any. The sine function acts like a bracket. So when isolating for B, when we take a look here, there is no subtraction or addition. It's just multiplication and division. So let's take a look at side B. Side B is on the denominator. So that is effectively division. The opposite of division is multiplication. Hence, we multiply both sides by B, and that's where B gets up to the top there. Now, we deal with sine. We treat sine like it's a bracket. So the opposite of sine is sine inverse. The other term for sine inverse is arcsine. That is a more antiquated way of saying sine inverse. However, there are some academics that still use both terminology, so I will use them interchangeably. So arcsine and sine inverse are equivalent. So at this point, we have angle B isolated, which is equal to the arcsine of B sine angle A over side A. It's at this point, once we get to this point here, then you're allowed to substitute in. So substituting in our values, we should get an angle of 38.79 degrees, assuming 4 sig figs. So now that we have angle B, the next logical thing to do is to find angle C. The easiest way to find angle C, and what makes the most amount of sense, is to use the sum of the angles in a triangle theorem, or SATT, which simply means that angle A plus angle B plus angle C is equal to 180. So isolating for angle C, again, doing Bedmas in reverse. To move these terms to the other side, they are both positive. When you bring them to the other side, they become negative. And then finally, after substituting, once we have the algebra done, we substitute in, and we're left with 71.21 degrees. So at this point, we have solved for angle B, we have solved for angle C. The last thing that is remaining to do is solving for side C. There are two ways to solve for side C, and we're going to explore both methods. We're going to use Sine Law first, and then we're going to follow that up with using Cosine Law. So when using Sine Law, if you noticed, I used the information for side C and I compared it with side A. The question is, why didn't I use side B? Because we had that angle. And if you read the note down here, there's a reason for that. Since angle B was found, there does come the possibility that there was an error in the calculation. So this number automatically is going to have rounding error in it. But in addition, we could have made a mistake in our mathematics up here. So as best practices would dictate is that you try to avoid using any found value and you try to stick with the most pristine. So in this case, the most pristine values to work with are angle A and side A. And the reason why is that those are given. So those have absolutely no error in them whatsoever. So this is why I'm comparing side C, angle C, with side A, angle A. So again, working with Bedmas in reverse, we don't have any addition and subtraction, but we do need to get rid of the sine C, and that sine C is in the denominator. The denominator is the same as C divided by, the opposite of divide by is multiply. So when we bring it to the other side, we have now isolated for everything. For side C, we substitute in and we get a value of 30.22. Now this time, we're going to do it using cosine law. Well, which version of the equation should we use? Well, since we're looking for side C, this very first version is the best one to use. So again, our goal is to isolate for C. So since it is C squared, and if we look at the rules of SAMDEB, we don't have any subtraction or addition, no multiplication or division, but we do have an exponent. So the opposite of square is square root. So we take the square root of both sides and we are left with this over here. Now substituting our values in, 30 for side A, 20 for side B, 30 for side A, 20 for side B, and angle C. Now, here's the thing. This is for sure going to have some error, but there's no way around it. So no matter what version of the we use, sine law or cosine law, there is going to be some error. The question is whether or not the amount of error that we have is acceptable or not. And generally speaking, if you try to stick with as much as the original data, the given data as possible, this is the best possible result. We have no other option other than to use this value here. And as a result, we're going to get the best possible that we can get, but also be aware that there is some error associated with it. Calculating this value, we do end up getting the same 30.22 to 4 sig figs. The next topic of discussion specifically is related to sine law. Sine law is the easier of the two mathematically to manipulate, but sine law does have a limitation. And there are some circumstances where sine law will actually report an incorrect angle. And the reason has to do with the nature of sine. Sine is only able to produce values between 0 and 90 degrees, where cosine is able to handle the full range from 0 to 180 degrees. So that means if you are working with a triangle that has an obtuse angle in it, working with sine law can be problematic. And let's take a look at this example and see if we can explain why. So when we look at this triangle here, it does seem, based on the shape of the triangle, that angle C should be larger than 90 degrees, should be greater than 90 degrees. And if it's greater than 90 degrees, we call that an obtuse angle. So in our triangle, here's what we got. We know that angle A is equal to 30 degrees. Side A has a magnitude of 30 and side C has a magnitude of 50. So if we want to solve for angle C, we're going to be working with sine of C over little c, sine of A over little a. So our goal is to isolate for angle C. So little c, or side C, is on the denominator, which means it's division. The opposite of division, of course, is multiplication. So that's where it comes onto the other side there. Then we need to get rid of sine. The opposite of sine is sine inverse, or arc sine. At this point, we've isolated as far as we can go. The next step is we substitute our values in. Now, when we substitute these values in, and be very careful to make sure that your calculator is in degrees, not radians, you're going to get a result of 56.443. The problem with that is this clearly does not look like an acute angle, but sine law, unfortunately, reports this angle here, which demonstratively is an incorrect result. So why does it do that? What's the issue? This is where we get into what is referred to as the ambiguous case up here. So when we talk about it being ambiguous, the problem is what your calculator, quote unquote, sees versus what you are seeing. Your calculator doesn't actually see the picture of the triangle. Your calculator only sees these numbers here specifically. So I'm going to draw you an alternate looking triangle that actually has all the same specifications as our original. So let's take a look here. So here is the original triangle in black, but I've added some new lines over here. So what I've done is I've taken side A and I've actually scooched its angle out like this. So now this is our new side A, and over here, our side B is much larger now. So when you look at it from this perspective, here is what is unexpected. In this version of the triangle, and specifically, we're talking about this, and this triangle here. When we focus on that, angle A is still 30 degrees. Side C is still equal to 50. And side A is equal to 30. The exact same parameters as we had up here, but the triangle looks very different. And that's the issue with sine law. Your calculator has no idea if it is working with this triangle here or if it's working with this triangle here. It has no idea. And the reason why it has no idea is because B is unknown and side B is also unknown. And as a result, it is ambiguous as to which version it is. Your calculator will always assume it's the one with the acute angle. So this angle C versus this angle C prime. So when you get this 56.443, that's referring to this angle here. Actually, let's be consistent. Be consistent with the colors there. Okay, so that angle there is 56.43. Forgive me, 56.443. All right, well, since this is an isosceles triangle, that means this angle in this corner and this angle in this corner are the same, which means this angle here is actually the supplement to this angle here. And what are supplementary angles? Supplementary angles are angles that add up to 180 degrees. So the sum of angle X plus angle Y is equal to 180 supplementary angles. So in our case, our angle C is actually 180 degrees minus 56.443. So 180 minus 56.443, and we get 123.6. So this is a problem when working with sine law specifically. So the big question is, what do we do about it? All right, well, first of all, let's talk about when sine law is safe. So sine law is safe to use when the angle you are looking for is not opposite the longest side. The only angle that has the potential to be obtuse is the one that is opposite the longest side. So if the angle that you're looking for is not opposite the longest side, you're totally good. Also, if there is already a known obtuse angle in the triangle, you can only have one obtuse angle in a triangle. And the main reason why is because the sum of the angles inside a triangle only add up to 180. To have an obtuse angle, you need to exceed 90 degrees. So therefore, to have two obtuse angles, both angles would have to exceed 90 degrees, which of course would automatically make it not a triangle because you would automatically go past 180. So only one angle in a triangle can be obtuse. So what are the best practices here? If you are running the risk of having an obtuse angle, here are your options. One, use cosine law instead. If you can use cosine law, and if you have enough information for cosine law, so cosine law, never a problem, because cosine law has no problems with obtuse angles. Cosine law can handle 0 to 180 degrees. Or alternatively, you can use sine law, but to find one of the other unknown angles. If the angle that you are initially trying to find has the possibility of being obtuse, then you guaranteed that the other angles that are in there have no chance of being obtuse. So let's take a look at our triangle up here. The only angle that has any potential whatsoever of being obtuse is angle C. That's the only one because it is opposite the largest side. Now, if we're talking about B here, in this case, I made it much more difficult to figure out. But let's say side B, let's say that was given as 15. So if side B had a length of 15, which it doesn't, but if it did, we know that 15 is not the longest side, and therefore side B, angle B I should say, would be totally safe to use sine law. There's no chance that B could be an obtuse angle because it is not opposite the largest side. So then if we were able to find B, then we could just use some of the interior angles in a triangle because we would know this, we know that, and then we could easily find that. So those are your two options.